morning. Let's continue on the system properties. Okay, so we have started on system linearity. We had an example, but we didn't quite finish. Let's finish that. Right. And maybe go through an example. And then we'll get on to the last system property, which is a time-invariant and time-variant system, okay, TI system. Just a quick review on system linearity. A linear system must satisfy the following two properties. First one is additive property. If a system has an input x of t, it produces y of t. We use m as an operator representing the system. If x1 is another input, it will produce y1. x2 is another input, it produces y2. Additive property basically says when your input is a sum of x1 and x2, then it should be the same as adding up the system outputs when they are given separately individually. So x1 and x2. And that is additive property. Okay. The next property is called homogeneous property. And this property basically says if you change your input to a multiple of the original input, so c times x of t, so scale it up or down, it should be the same as you scale up the output when the input is x of t. So that's homogeneous property. And there is a property that can combine these two together, which is called the superposition property, right? So combine one superposition, and this property says when you scale up x1 and x2, and then put them as a new input, so it should satisfy the following writing. So that's a quick recap of what a linear system is. To check system linearity, essentially to check whether the system satisfies the two properties or not, or whether the system satisfies the superposition. So you could, when you're conducting the checking, what I have recommended, right, is go through this additive and homogeneous property, okay, instead of going through the superposition property. As long as one property is not satisfied, then the system is not linear. So that's the idea. So in the last lecture, we did an example, which is system is given by x of t minus 2 plus x of t 2 minus t. So we want to know, is this a linear system or not? So I didn't finish the question, but what I did finish in the previous lecture is I have checked the additive property. So we checked the additive property from previous lecture. Which it has gone through. So the system satisfies additive property. Okay, if you recall that, you can look at your lecture notes and see how that was conducted. So let's finish this by check the homogeneous one. So let's check the homogeneous property, and this is actually a much easier property to check for this example. Okay, so this one has checked out. We just need to satisfy the homogeneous before we can draw a conclusion. So homogeneous property, basically, as we listed here, we need to check the left side and the right side and to see if the equal sign holds. If it holds, perfect, it's homogeneous. So let's examine this one first and then look at this one next. First, let's look at m c times x of t. So mc times x of t. Essentially, you're changing your input, right? So the original system is this. So that's basically when your input is x of t, your output is this, right? And now your input is changed from x of t to cx of t. So it's actually pretty simple. All you need to do is what? Replace the x with c times x. So this just becomes c times x of t minus 2 plus c times x of 2 minus t. That's a replacement. So at this stage, and according to my experience, and I find it's a game you're playing with your brain, basically to see which one of you will actually win. It's a replacement, because sometimes, you know, when I ask you, for example, very simple ones, right, saying replace the x with 3, I think you will win. But when it comes to more of abstract like this, and doing the replacement, often in time there's some kind of force will fight with you. Okay, that's where you need to get comfortable with, actually, in terms of replacement. We'll see a few examples next. Okay, so that's the left side of the homogeneous property, and then we look at the right side of the homogeneous property, which is the c times m of x of t, and that seems to be also very straightforward. You just using c times the original output. Of course, in this case, they are literally the same. So homogeneous property is checked. Both properties checked out. Then you can draw a conclusion that the system is a linear system. So I want you to exercise one yourself before I'll finish another example, but I want you to exercise this, okay, yourself. So let's say you have a system y equal to x squared. And this is a system parabola, producing a parabola. When you enter the system with x of t, it'll spits out y equal to x squared of t. So I want you to go through the steps, okay, like what we did. Essentially check the additive and check homogeneous, verify if this is a linear system or not. In this case, you actually probably will only need to go through one step. If you check the additive, you probably will stop there. You'll see the additive is not satisfied, and you can stop there saying the system is non-linear system. Okay. So I want you to do it yourself. It's a very simple one. But I will go through in the next example, okay, with you. So let's look at this system here. I think I have actually listed this system. So if the system is a very simple system, which is basically d over dt here, this is what we call a differential operator, right, or derivative. Okay, so the operator here, this is m, and m in here is a differential operator. And the idea is a differential operator a linear system or not? Or in other words, is this operator a linear operator or nonlinear operator? Okay. Yeah. So we go through the same thing and to verify this linearity. First, additive property. Additive property has one left side and one right side. We check the left side, meaning we change the input from x1 of t, x of t to x1 of t plus x2 of t. Okay. And because this is an operator, right? So it operates on whatever the inputs, and you plug it into the big brackets there. So the operator basically will operate on this new input, which is x1 of t plus x2 of t. Okay, and one of the property for a differential operator, when you're operating on a bracket which has multiple terms in it, you can literally just expand it, right, as it is, as like multiplication. So this will become d over dt x1 of t plus d over dt x2 of t. Okay. So basically, the derivative operates on each one of these separately now. And the other side of the additive property is the separate operation or separate inputs. Input x1 and x2 separately, and then we try to add them together, see what they equal to. And this is equal to d over dt x1 of t plus d over dt x2 of t, which is the same as the other side. So you can conclude that additive is satisfied. Okay, that seems to be very straightforward, right? Okay, so then you go on with homogeneous. I cannot emphasize more important at this stage when you do assignments or when you do your writing, even though this course does not have assignments. But I still strongly encourage you write on your own piece of paper instead of just look at the solutions. Okay? I believe I posted first assignments, but I haven't posted solution yet. So practice first. When you practice, do it as if you're doing an exam question. So when you write, try to write, okay, some comments, okay, some of the steps that are here. This is what I noticed actually nowadays when I teach my kids math. And one of the habits you all have is they write everywhere, right? And also they write just a number, right? You know, when you ask where it's from, it's from there. So you know where it's from, but after a few while, where it's from? I don't know where it's from, right? So you write a few more details, it'll help you, okay? Sometimes I skip the detail, but don't follow me, but I want you to write more details you watch, okay? M of homogeneous. So we check, first we check what this term equal to. So mcx of t, and that equal to d over dt c times x of t. Right? That's the differential operator operating on c times x of t. You can take the c out of the differential because it's a constant. So that's the left side of the homogeneous property. And then the right side of the homogeneous property is c times m of x of t. And that is directly just c times dx over dt. So that checked out too. So both checked out. The system is linear. Okay. So in other words, differential operator is a linear operator. Okay. If you use this operator represented as a system, then it's a linear system. Now, if you recall in the previous lecture, I mentioned quite a few operators that you will learn in this class and also in my other class, and possibly in the future in many other classes. Okay? Yeah. Now, the operators, if you look at your lecture, the operators I listed actually will turn out they're all linear operators. Okay? They're all linear operators, like Laplace, Fourier, the grading operator, the curl, the divergence operator, they're all linear operators, just like this one here. You can also check the integration operator, and it's also a linear operator. Okay? Okay, so that is another example of checking linearity of the system. So in my lecture notes, I have a couple more examples to check whether a differential equation is a linear system or not. I think I'm going to keep that until when we touch the differential equation. Okay? So if you recall at the first lecture, I said, one big part of the course is about learning differential equations which is used to derive the dynamics of the system. There are different kinds of differential equations. There's a so-called ordinary differential equation. There's also so-called linear ordinary differential equation and a nonlinear ordinary differential equation, right? And to differentiate those, the additive or homogeneous or the superposition is actually the rule we follow to differentiate what type of differential equation they are. Okay? So that we'll touch upon that in the near future. Okay. Any questions on system linearity? All good? Okay, so let's look at the last type of a system, classification of the system. That is time-invariant or time-variant system. Time-invariant, we often in time short to call it in short a TI system. As a matter of fact, once we finish this classification, we can combine the linear system and time-invariant system together. We have a very special system which is called linear time-invariant system, okay, LTI system, very common system. Okay. So first, let's look at the definition of time-invariant system. As usual, we will have our regular system whose input is x of t, and system represented by operator m, output is y of t. The formal definition says this: the system is TI, time invariant, if and only if, okay, for any kind of input x of t and any value t naught, constant value t naught. So for every kind of x of t and any value of t naught, the output corresponding to x of t minus t naught. So basically, the input is not x of t anymore. The input becomes x of t minus t naught. The corresponding outputs, okay, will be y of t minus t naught. If this is satisfied, then the system is a time-invariant system. Okay, so that's the formal definition of TI. So if I look at this one here, before we look at the example, so let me write down this here. So when you have a new input, the new output is this. So if you look at the definition, let's describe it with a little bit more informal language. Basically, originally this is your system, right? You can't change that. That's whatever the system is. Then the manipulation is you give the system a new input. The new input, the difference between the new input and the original input is what? What's the difference between these two? Minus t, but mathematically minus t naught means, in your first tutorial you learned, we shift to the right. Yes. So this x of a t minus t naught, right, is the shifted version. And you're shifting to the right by the amount of t naught. Of course, if t naught is less than 0, then you're actually shifting to the left, right? Yeah. So basically, you change the input with a shifted version of the original input. Then what happens if the system is a time invariant? Then according to the definition, the output, the new output, right, corresponding to the new input, is nothing really, well, it's different. It's nothing special, but what, compared to the old one, it's a shifted new output, right, based on the original output. And the same thing, you're shifting it to the right by an amount of t naught. So basically, if you have a shifted input, okay, then the output is also shifted with the same amount. Okay, then your system is time invariant. That's basically what it says. Graphically, here's more or less what it means. So let's say, for example, if you have a very simple input, maybe it's a line, linear, a line at here, okay, and you give it to the system, and the system is a time invariant system. So the output, I don't know what it is, but that's assuming the output is this. Okay. So this is the input-output relationship. Now, if there's a question saying here, okay, so I'll give you a new input, and the new input, okay, is basically a shifted version of the original output. And if you're required to derive for the new output, okay, if you're required this, let's call this as a new input. Let's call this x1 of t, right? Because it's different from the original one. And this will become a y2 of t, a y1, y1 of t. So the shortcut set here is, if you already know that the system is time invariant, your original output maybe is derived from a certain differential equation, right, mathematically. But now, if you know your input, your system is Ti, then you can skip all of the other efforts. You can see, okay, so if this is a Ti, this is a new input, guess what? My new output will be just shifted version of this original output. Okay? That's basically what it means graphically. Okay. So I'll show you a couple of examples that are here. Okay. And I'll explain a little more regarding this time variance and time invariance. Okay. Let's look at the first local example here. Let's see, if I have a system which is y of t equal to t times x of t. So basically, not sure what's exactly going on within the system, but if you give your system input as x of t, it will spit out t times x of t. And I wanted to check if this is a linear, if this is a time-invariant system, or is this a time-varying system? Okay. So to check, essentially what we do is this. We will look at the left side of this property. We also look at the right side of the property. And then we compare, draw a conclusion. Okay. So check. First check m x of t minus t naught. Okay. Check this one first. Good. And I find often in time it's a bit of helpful if you can define temporarily a function, right? Before you insert everything into this big bracket. So maybe we can let a function, let's call it xd of t equal x of t minus t naught. So let x of d equal to this new input. Okay. You can name it anything you want, okay, as long as it's different from your x. Now your m x of t minus t naught essentially is m of x of d now. So give a system a new input, which is x of d instead of x of t. According to the given system, if the system becomes xd of t, the system output should be what? Exactly. Good. That's right. That's a replacement you're looking for. You're replacing the x with x of d, right? Yeah. And now you can put this x back because you know what the x of d is. That's what you define, right? So you can just t times x of t minus t naught. That's your x of d of t. And that basically is your left side of the time invariant property. So now let's check the other side, which is y t minus t naught. Okay, check the right side of the property, y of t minus t naught. Y of t is given. It's a t times x of t. So y of t minus t naught here means what? You're replacing this t with t minus t naught. It's like this is not a specific number, but it's very much the same as, can you replace the t with 3, right? Except here's t minus t naught. So what do? You're going to go to the expression for the output and look for t. Look for every one of the t, replace every one of them with t minus t naught. So I got t here, I got a t here, so that becomes t minus t naught and x t minus t naught. Okay. So this is the right side of the time invariant property. So then you can compare these two. They are not the same, right? They're not the same. The difference is here's t, here's the t minus t naught. Okay. So then you can draw a conclusion. Hence, this is time varying system. Okay, this is a time varying system. Okay. So as a matter of fact, okay, if I show you an example, but I probably won't go through it, but let's just see if I have another system which is cosine t times x of t, for example. Okay. Let's see if you have another system. It's cosine t times x of t. The only difference is the other one is t times. This is cosine t, right? Yeah. But the similarity between these two systems, what? The similarity between this system and this system is that you have a function of a t which is not part of the input. Okay, this is not part of the input, right? That explicitly presents itself in the output. So you see here, you have a t showing up explicitly, you have a cosine t showing up explicitly, and either one of them is part of the input. Okay, in both of the examples. If you go through the steps that I just done here, you will see that this is also a time varying system. Okay, this is also a time varying system. The reason is because exactly what I just said. Because in the expression for the output, there is a time function explicitly present itself, and that's not part of the input. In this case, and you can actually often confidently make a conclusion that this is a time variance system. Okay. So basically, when t explicitly shows itself, but remember the t is not part of the input. Okay? It's not this t. Okay, this t is this is your input t. That has nothing to do with this, right? Yeah. The system is time variant. So this part is different from this part, just like this part is different from this part, right? So this is your input. That's also a time function, right? Yeah. But this one here is a time function, but that's not part of the input. Yeah. So the statement here is, as long as you see an expression here times this, for example, right? It's part of the not part of the input, but it's a time function, and chances are this is going to be a time varying system. Okay. So, for example, I'll give you a not so rigorous example here. Okay. Let's say you have a car, and the car are supported by 4 springs, right? So mechanically, this is a typical what we call basically mass spring damper system, and there's also damper in the car, right? Yeah. So when you model this system, you have a spring which has a coefficient called stiffness of spring. You have a damper, you have a coefficient called damping. And you have the car has a total mass on top of these 2 systems. Okay, so you can derive an equation describing the system with the parameter of the spring stiffness, with the parameter of the damping ratio, damping coefficient. Okay, yeah. But when you drive the car for, let's say, maybe after 5 years or even after 10 years, what do you experience? The car becomes what? A little softer, right? Yeah. So basically, as time goes on, the spring is less rigid now. The spring stiffness changes. So if your system output contains that spring stiffness parameter, we usually call that K. Okay. It's a time parameter basically. As time goes on, the parameter changes. So that system is exactly what we have just called here. It's a time varying system. Okay, it's a time varying system. So there are parameters in the system that's time dependence. If that's the case, and this is typically an example, this is a time varying system. Okay, time varying system is the opposite side. The parameter of the system not supposed to change. It's supposed to be a constant all the time. All right? Yeah. Okay, so I think I can go through another example here. Okay. We'll use that example that we have done for the system linearity. Okay, so let's use this one because we show that this system is what? It's a linear system, right? Yeah. So let's check if this is a TI system or time-invariant system, a time-variant system, TV system. We go through exactly the same approach. We will check first when the input becomes a shifted input, okay, x of t minus t naught. So I'll use my supplemental variable, introducing a supplemental variable here temporarily. So we're going to let xd equal to this new input, x of t minus t naught. Then when your input is xd of t, according to the given system, right, your output of the system will be, essentially you're going to replace the x with x of d, xd here. So that basically becomes xd t minus 2 xd 2 minus t. Okay, but we don't want xd here, right? We want the x here. So now you go back to your expression for xd of t. Here's your expression for xd of t. So I want you to very carefully look at what replacement you need to do, okay? So xd of t equal to this. Then what is xd of t minus 2? You're replacing the t with t minus 2. Excellent. So you basically replace this t with t minus 2. You don't touch the t naught, right? You keep it as it is. This is your xd of t minus 2. And then the next one here, you replace the t with 2 minus t. Yeah. So now you get this, right? Yeah. Oh, so not the xd naught. Yes. Thank you. Good job. Okay. Yes. Oh, sorry. Yes. It's what is it? 2 minus t naught, right? Yes. Oh, sorry. What did I do right? Sorry. Here is a t minus t naught. Replacing the t with sorry, what's going on here? I'm not following the. So replace the t with 2 minus t. Okay, that's all right now. Right, replace the t with 2 minus t. So 2 minus t minus t naught. Here, replace the t with t minus 2. So t minus 2 minus t naught. So that is thinking here, right? The replacement, the proper replacement. And this is basically when your input becomes x of t minus t naught. Okay? I'll let you thinking here, okay? This is the left side, and now we have the other side, which is y of t minus t naught. Any questions so far? I know this is the part that I often find students have confusions. It's all clear? Yeah. It's okay, because if it's not clear, it's just let it sink in. Okay. Output shift by amount of t naught to the right, and that's when it's actually usually easier. You basically replace everywhere the t with t minus t naught. So that gives us x of t minus t naught minus 2 plus x of 2 minus t minus t naught. Okay, this time, this one to be careful. Huh? You put in the bracket. You're replacing the t with t minus t naught. Yes?
So why would you do that for the first one?
For here?
Yeah.
Yeah. So observe the replacement, right? So maybe let me write down separately here. So let's say this is xd. Okay, right? And this is xd 2 minus t. Okay, right, that's the part. If this is your original, this is the new one, how do I manipulate, right, to get the new expression? So the difference, always observe the difference. The difference is you're replacing the t with 2 minus t. So all you need to do is you go to the other side, go to the right side, look for the t variable, and replace the t variable as a whole with whatever inside these brackets. So t, there's only one t at here, so you replace that t, right, with 2 minus t, and that's what I write at here, right? Yeah. Is that good? So now you can check these two out of here. Okay. Don't be confused that they look like the same actually. Okay. Especially the first term. Look at the first term. This is t minus 2 minus t naught. This is t minus t naught minus 2. The first term checked out, right? First term. But the second term at here, this one is x of 2 minus t and then plus t naught. So that's subtle difference, right? Basically tells you that this is a what kind of system? Time-invariant system. Right. It's a very wicked example, but I think it's a good illustration how to properly, right, prove, how to properly substitute. Okay? Yeah. So maybe I'll give you a concrete example here, okay? Let's say let's suppose I have a system xd of t equal to x of t minus 3. So t minus 3 basically means I probably have a t minus 3 squared and t minus 3 like that. This is how you write function of t minus 3, right? Because you have a common t minus 3 terms at here. That makes sense, right? So according to what we're doing here, if typically you say, okay, can you replace the t with, let's say, a 4? Right? What do? You find the t here, replace that with 4. Right? Yeah. But except that here we're replacing the t with what? 2 minus t. So basically, you're replacing it with, instead of a number, you're replacing with another expression. So I'm going to find the t at here. Right, to do this replacement. So that's what happened in the background, right? Except here we're not really having a specific function, we're just generic x of t, xt minus 0. Okay? Any questions? I think this is the part you need to have a little practice to let it sink in here. Okay? the proper substitution, and always write a few more steps. Follow this, check that, and then draw a conclusion. Okay? So, as I said, I posted the first assignments. You don't need to submit the assignments, but you are expected to exercise before the solution is posted.